No, great. What I would like to do is, if you have questions, you should post them in the chat, and I'll try to monitor the chat window as we go along here, just to keep things going. I'll probably stop occasionally for a sip of water, and I'll take a question then. Okay, so the title of and let me just say that I'm pleased to be here at the Argonne training program on extreme scale computing. I'm a frequent visitor. I think I've been coming since since 2014. I think I missed the first year. And I'm sorry that we can't be together in the same room, because it's much more enjoyable in that setting, but perhaps on another occasion. So I'm going to talk about benchmarking, and I'd like to talk about my beginnings in benchmarking. I'd like to think of myself as an accidental benchmarker. And I actually began in 1973. I was an undergraduate in 1973, and I was selected to come to Argonne to spend a semester. I spent my last semester as an undergraduate there, and that's a picture of me in 1973. And I sort of stuck. That is to say, I stayed at Argonne for a number of years after that, leaving in 1989 to come to Tennessee, where, as Lois mentioned, I'm at the University of Tennessee and hold a position at Oak Ridge National Lab, and spent a little time at Manchester. So I've been doing software for just about 50 years. And this project called ATPESC was the first project I started on. ATPESC was an effort at Argonne National Lab and had colleagues at other places contributing to it. It was designed to be a software library for computing eigenvalues and eigenvectors of matrices. It was written in Fortran, Fortran 66. It was based on an ALGOL set of algorithms. So there was a book published. It's a thing in the lower right-hand corner there called Linear Algebra by Wilkinson and Reinsch. They edited this book. It is commonly referred to as the handbook for linear algebra. And it contains the state of the art for finding eigenvalue problems in the early 70s. And our job in ATPESC was to translate those ALGOL algorithms, programs into Fortran, so they could be usable on some of the machines that we had within the Department of Energy and also at other places in the US. Those algorithms drew heavily on the work of Jim Wilkinson. About the same time, there was a set of routines that were being created by the community. And those routines go by the name of the BLAs. At that time, there were just level 1 BLAs. And those BLAs were vector operations. So we had things like dot products and AXPs, a scalar multiple of one vector added to another vector, and a bunch of other things for computing norms and scaling and so on that were around. So there was a standardization process to create a de facto standardization to create a set of low-level routines to do vector operations. ATPESC predated the BLAs, so ATPESC doesn't have any of these things. It's just straight Fortran code, and we respected the ALGOL. The ALGOL, it was just a transliteration almost of the ALGOL into Fortran. Some of you remember ALGOL or know something about the history. ALGOL organized its matrices not by columns the way Fortran does, but by rows. And the Fortran routines that we wrote respected the ALGOL organization by rows, and that led to some inefficiencies in the algorithms. The first paper I published was in 1979, and that was about unrolling loops in Fortran. So the idea here is to take a loop. On the right side here is a loop for doing an AXP. So we've got a scalar multiple of a vector added to another vector, and there's a loop around that. And the insight in this paper was to unroll the loop. Now we take this for granted today. In fact, we expect the compiler to do this for us. But back in the late 70s, that was not the case. This was sort of a novel idea to unroll the loops. The unrolling had the ability to facilitate any pipelining that was there in the hardware. It also increased the level of concurrency that could be exploited by perhaps independent functional units. And we were able to get about 15% improvement on the performance of that simple loop by doing this kind of unrolling. Omitted from this scrap of code here is the cleanup. So if things were not divisible by 4, there had to be a loop to clean up and take care of the bits at the end. That was written up in a working note, something called the LINPACK working note number 3 about Fortran BLAS and how to do this unrolling. And I gave extensive information about the timing for these things. And about this time is when the BLAS publication first appeared. So there was this basic linear algebra subprograms that Lawson, Hansen, Kincaid, and Crow published, and they actually used my implementation in their realization of the codes that they were specifying for the standard. So that's how I got started. I was interested in performance and linear algebra, and extracting 15% was a relatively big deal at that time on the scalar machines that we had available to us. So about that time, the BLAS were being finalized. We created a package called LINPACK. So LINPACK was started in the late 70s and saw light about 1980. And it was a set of routines for solving systems of linear equations based on these level 1 BLAS. So we structured the codes in LINPACK to use these vector operations whenever possible. And because we were writing in Fortran, we organized things by columns, not by rows, to extract additional performance. So I became an accidental benchmarker about this time. LINPACK was a project that was funded by the National Science Foundation and the Department of Energy. There were 4 main contributors to it. So from the right there is Jim Bunch. He was at the University of California, San Diego. Next to him is Pete Stewart from the University of Maryland. And then next to him is Cleve Moeller from the University of New Mexico. And I'm the guy there on the far left with that little bit more hair than I have today. That's my car and my license plate. I was a student at the University of New Mexico at the time when we were doing this project. So LINPACK was a package of software for doing systems of linear equations. We produced a user's guide, and one of the things that I did was to produce a tape or an appendix in this LINPACK user's guide, which estimated the runtime for solving a system of equations. And in that appendix is this table of 23 machines for solving AX equal B. So I set up a matrix problem. A matrix was of size 100. 100 was used because I could fit it on all of the machines that I had access to, all of the 23 machines. And I ran that system of linear equations from LINPACK. And this is the table, and the scribble that you see there is my calculation to translate the time to solution into a rate of operation. So that first machine at NCAR was a Cray 1, and the Cray 1 was getting 14 megaflops for solving that system of linear equations using this LINPACK software. So that's the origin of the top 500 list, I'll say. It consisted of 23 machines that was published in the LINPACK user's guide. The code that was run is listed here. So the code fits on one page. The routine that factors a matrix is called DGEFA, and it has it's Fortran code. It has an outer loop there on K. There's a middle loop there on J, and the innermost loop is actually a call to DAXB. So DAXB again is taking a scalar multiple of a vector and adding it to another vector. There's some additional code here for doing partial pivoting. So pivoting is important in an LU factorization. It's there to produce a stable algorithm to avoid any kind of degeneracies and growth that may occur. So we search down, find the largest element, scale the column, and then go through a swapping operation before we apply that DAXB to the column. And the cartoon, the number of operations that this algorithm consumes is 2/3 n cubed operations plus something order n squared. So we characterize the algorithm as order n cubed operations, 2/3 n cubed to be more precise, going on in that code. And the cartoon version of this algorithm is it takes a scalar alpha times the pivot column, and it multiplies that pivot column by that alpha, and then subtracts it from the kth column there of the matrix. Updating all the elements in that submatrix is the way this algorithm proceeds. And that fundamental operation there is that Daxby operation that goes on. So we're factoring a matrix, and then after the factorization, we do the solve. And again, pivoting is sort of a critical element of this method. If you don't do pivoting, you're going to get the wrong result unless the matrix has some rather special characteristics. So pivot's there. The pivoting is there to avoid zeros or small numbers. That's called degeneracy. But more importantly, it's there to avoid growth in the algorithm, in the elements of the matrix, which would produce a loss of accuracy. So we take a matrix and we factor it into these L and U components, a lower triangle and an upper triangle. And then we solve a system based on those parts. We solve two systems. We solve one based on L, and then to get the final solution, we solve the part based on U. And that, again, that consumes about 2/3 n cubed floating point operations. And this particular algorithm touches the matrix there's 2/3 n cubed touches to the matrix in this particular implementation. So this is not the most efficient implementation, and I'll show a way to make it more efficient in a moment. But there's 2/3 n cubed operations and 2/3 n cubed touches to the matrix. The rate of execution is the thing we're interested in, and that's the number of operations that you perform divided by the time it takes to solve the problem. And that gives us a rate, or in our terminology, it gives us the number of flops, floating point operations per second. And again, something to note here, and something that applies to all modern computers, is that doing fewer flops does not always translate into less execution time. So data movement is very important. So the less communication that you do, the better off you're going to be in terms of efficiency of the algorithms. So LINPACK benchmark that was put together was portable. It runs on any system that has a Fortran compiler. It's fairly easy to understand. It produces one number, the rate of execution, the floating point operations per second. That's sort of the output of this routine. And the benchmark itself says that the algorithm is fixed. You have to do LU decomposition with partial pivoting. You can't use some fancy algorithm. You can't do something else to it to find the solution. You have to use that method because we can guarantee the number of operations. We allow for restructuring and optimizing the code. All of the operations have to be performed using 64-bit floating point arithmetic. And we check to see that you get the correct solution. And the correct solution is done by this backward error. We take AX minus B, we compute a residual, we compute the norm of the residual, and then we divide it by the norm of A times the norm of X plus the norm of B. And that should be a small number. That should be around machine precision. Machine precision, if you're working with 64-bit floating point, is around 10 to the minus 16. And we can then think about multiplying this by that epsilon 10 to the minus 16 to convert it to a number that's around 1. So as long as that benchmark check or that residual check is around 1, when it's normalized in that way, we say that you've got the correct solution. And again, this is not, this benchmark was never intended to measure the complete machine performance, just to do this one very specific problem. So it's important to understand the timing when this benchmark came out. Back in the 80s, floating point arithmetic was very expensive. So that was the thing that cost the most. So we were trying to capture that quantity and hopefully reflect what it would take to solve other problems on other machines based on this kind of fundamental operation. Let me just pause here for a sip of water, and if somebody has a question, please shout it out. I don't seem to have my chat session up here in this window, unfortunately, so I can't see my chat. Okay.
There are no questions in the chat.
Thank you. I'm going to carry on then. Okay, so the LU decomposition, as I've described it, has evolved. And instead of working with columns of the matrix, today we think about working with panels of the matrix. So instead of having the kth column and doing something to it, we think about taking a panel of these subcolumn called B, and then we do a factorization on that sub panel. So we actually perform a LU, while we're doing the LU factorization of the matrix, we do a LU factorization of the panel B to find its LU factors. So the matrix does not have to be squared to do an LU factorization. We do a factorization of the matrix, and then we apply those pieces to the rest of the matrix, to that submatrix, to that trailing submatrix to update it. And if you're thinking about how this works from a linear algebra standpoint, we basically do a set of transformations which will introduce zeros into that panel B, and then the second part applies that sequence of transformations to the submatrix called E in this case to update that matrix. So that's sort of the standard way of doing that. And if you do that, it turns out that you can uncover a matrix multiply in that operation. It's actually a rank K update. So we're taking the matrix E and we're updating it with a rank K matrix. And that rank K matrix is composed of this matrix L1 and U1 here. That's updating or modifying the matrix E. And we can express it as a matrix multiply. Matrix multiplies are the good guys, I'll say. Matrix multiplies, have this characterization of doing n cubed operations and order n squared data movement for a square matrix. So we get this surface to volume effect. So we have n cubed operations and n squared data movement. So that's the right balance that you want to have when communication, when data movement, when touches are an important part of the efficiency equation. So doing this algorithm can enhance the efficiency, and it does exactly the same number of numerical operations. So we have not increased the number of numerical operations. We've converted something from a vector into a matrix multiply, and it has exactly the same numerical properties. So we can say something very strong about the characterization of this matrix. It has all of the characterization of the original algorithm. Around 1993, Hans Moyer, pictured here on the right, and Eric Strohmeyer approached me. They knew I had a list of these of benchmark numbers from doing the LIMPAC benchmark. They had a list of the fastest computers. They had a list of fastest computers based on the theoretical peak performance for those computers. And I had a real benchmark for those computers. And Hans talked to me about merging our two lists and coming up with a list of the 500 fastest computers based on that benchmark. So that's what we did. We put together our lists and had something called the top 500. That list appeared first in 1993, and there were 500 entries in that first list, quite surprisingly. And again, it was a list of the 500 most powerful computers in the world. That list has been updated every twice a year since 1993. It performs that basic operation, solving AX equal B using Gaussian elimination with partial pivoting. It goes through and computes the time that it takes to solve that system of equations and then converts that time into a rate of execution. And that rate is your entry point into the top 500 list. And again, that list is updated twice a year in the meeting that's held in the States in November. It's going to be held in November, just before Thanksgiving this year in St. Louis. And it's also, the list is also exposed in a meeting that's usually held in Germany in June. So the most recent data we have is from the June list. The fourth person in the picture is Horst Simon, who joined the group a few years after we got started. So you should have in mind that when you solve a system of equations on a computer, so this characterization here, This little chart here is trying to give you a characterization of what happens. As you increase the size of the problem, you'll get a new rate of execution. So it starts out small for small problems, and the rate of execution climbs until you get till you reach some asymptotic point. If you were to solve different problem sizes, you would see this. And the benchmark is trying to capture the asymptotic rate for your machine. So the highest performance it's trying to capture. So basically, you want to run the largest problem you can on your machine, solve it, take the time it takes you to solve that problem, convert it to a rate of execution, and that's the number that gets entered into the top 500 list. So the top 500 has been around for a long time. Here's sort of a timeline, if you will, for the benchmark itself. So in 1994, the LINPACK library was created. 1977, we had the LINPACK benchmark, which ran a matrix of size 100. It was Fortran. In 1986, I changed the benchmark to have a bigger matrix because we had faster machines at this point, and the matrix size was of size 1000. So we collected performance numbers for that. The first gigaflop computer, that is the first computer that reached the gigaflop for running this benchmark, was in 1988. That was an NEC SX2. And then the HPL numbers started to be formed in 1991. And that was the thing that really defined the top 500. So in 1991, you can run as large a matrix as you can, solving that problem using the best implementation of Gaussian elimination with partial pivoting, using all the features on your hardware to solve that problem efficiently. And then in 1993, the top 500 started. So the first computer, the number one computer, I'll say in 1993, was a computer at Los Alamos National Lab. And that was a thinking machine CM5. It had 1,000 processors. It ran the benchmark at 60 gigaflops. That was its rate. By 1994, all of the computers on the top 500 list were running over a gigaflop. In 1997, we had the first teraflop computer, and that was a computer at Sandia National Lab. It was called the ASCII Red computer. And again, it had lots of processors in it running the benchmark at over a teraflop. China makes its appearance on the top 500 list in 2001. The Japanese had a machine, very impressive machine called the Earth Simulator. It was number one. It was 5 times faster than any other computer on the list. And in 2005, we see all the computers on the list being a teraflop. The first petaflop machine was at Los Alamos National Laboratory in 2008. And then we had a sequence of machines. The first machine from China to be number one was in 2010. So the Chinese machine, the first Chinese machine on the top 500 was in 2001. And then 9 years later, they have a number one system on the top 500 list. Japan comes up with a machine called the K computer, very impressive architecture, which was number one. A machine at Lawrence Livermore with 1.5 million cores in it was there in 2012. The Tianhe 2 Chinese machine at 33 petaflops. And then in 2016, China and the US have equal number of machines on the top 500. So again, coming from in China, one machine in 2001 to equaling all the machines in the US in 2016 shows that China has really invested quite heavily in high performance computing. And then China produces a machine which is number one with about 10 million cores in it in 2016. Argonne, or Oak Ridge's Summit machine comes on the scene. And then in 2019, all of the computers are over a petaflop. The number one machine is the machine from Riken in Japan called Fugaku. That's still the number one machine today. China has 186 machines on the top 500, and the US has 123 machines. So again, China is dominating the top 500. And we expect to see the first exascale machine coming along sometime later this year, perhaps at Oak Ridge or perhaps in China. or early next year. So the betting would have it to be in November to have the machine at Oak Ridge running called Frontier at an exaflop. So that's the top 500. This is a list of the #1 systems on the top 500 over the past 27 years. So there have been 20 machines which have been #1 on the top 500. I mentioned the machine from Los Alamos lab, the thinking machine CM5 with 1,000 processors was the first #1 machine. What you're seeing here is when it was introduced, how long it was #1. It was only #1 one time. Its execution rate, the number of cores, the matrix size that it solved to achieve that performance, and the number of hours that it took to run the benchmark. So here it took just 20 minutes to run the benchmark. And as we go down this list, we see a number of machines. The US has had 10 machines at the top. Japan has had 7. And China's had 3 machines at the top of the list. It's interesting to note that the size of the matrix, so the matrix that was run on Fugaku was a matrix of size 21 million. So this is a dense matrix problem of size 21 million. It took about 4 hours, almost 4.5 hours to run that matrix. It consumed, so the amount of power that this machine is consuming while running the benchmark is around 30 megawatts. So 30 megawatts is a stunning number. So a megawatt year. So think of it like this. If you have a megawatt year, so if you had a computer that ran at 1 megawatt for a year, you would get a bill from the electric company, at least in the US, for about $1 million. That's what it would cost to power that machine, the electricity cost. So, that machine cost roughly $30 million just to turn it on to have these machines run. So they're very expensive, of course. They're very powerful machines as well that can be used. The Department of Energy, of course, has dominated the US in terms of its high performance machines. Their DOE is the only place that's had machines at the #1 position in the US. Los Alamos has had 2, Sandia has had 2, Livermore has had 3, and Oak Ridge has had 3. So left off of that list is Argonne. So Argonne has never appeared as #1, and also Lawrence Berkeley Lab has never appeared as #1. So looking at high performance computing, today we see that we have petaflop machines. We have all the machines on the list are a petaflop or greater. We see 3 architectures that are being used in the top 500. So the first architecture is just to use commodity processors. Get a bunch of commodity processors and connect them together using some kind of interconnect, and we're going to call that a supercomputer. Typically Intel processors. The second architecture trend is to use commodity processors plus an accelerator like a GPU. And of the 500 machines, 145 are composed of this kind of architecture. NVIDIA has the most machines. 138 of the 145 use NVIDIA GPUs. And the third architectural class are machines that use lightweight cores. So these are cores that don't have all the sophistication of, say, an Intel core. It doesn't have all the sophistication of caching, of all the intelligence that goes into predicting where instructions might come from in future, doing a number of things that these architectures do for prefetching things. They're very lightweight in scope. And we see 2 models there. The Chinese have a machine called the Tahu Lite, which have very simple architecture that's used to build their machine in the top 10. And IBM used to have a machine called Blue Gene, which is also based on this kind of architecture. So China's the top consumer of supercomputers and also the top producer of supercomputers. So when you look at the 500 machines, most of them are in China and most of them are made in China. Now they may be made with Intel parts, but they're coming from companies that are integrators in China. There's interest in supercomputing worldwide. About half of the machines on the top 500 list are in industry. So industry gets it. These machines provide some kind of strategic advantage and they're willing to invest in these machines. And Intel processors hold the largest share. So of the top 500 machines, 86 of them are based on Intel architecture, and 10% are based on AMD's architecture. So when you look at that, you would say 96% are based on x86 architecture. They may be using accelerators to boost the performance, but Intel has a real dominance here in terms of high performance computing. It'd be interesting to see if that carries forward into the future. We see exascale projects in many parts of the world today. This is sort of a snapshot, if you will, of the top 500 list since it began. So what we're looking at here is charting the red dots represent the #1 computer today. That's the Riken's Fugaku machine with 442 petaflops. It's been there 3 times. And looking back in time, this is the thinking machines CM5 at Los Alamos at roughly 60 gigaflops. This orange line here is charting the machine at the last position, number 500. Today, that's at 1.5 petaflops. And you can see back in 1993, the guy at the bottom was at 422 megaflops. And then the blue line here is the sum of the 500 machines. So that's an Excel sheet computation, just adding up the numbers. So we have about 2.8 exaflops represented in the top 500. So we see some interesting trends here. It's obvious that we don't have straight lines here. This line at the bottom, there's this inflection point that occurs somewhere around 2007. We have another inflection point that appears here in 2012. And people ask, what's causing that? So I think there's many causes for it. One cause is the slowdown of Moore's law. Moore's law is not ending, it's slowing down. Also the end of Dennard scaling, the ability to enhance the chip feature size and do that without adding, having a faster processor, without adding more power into the processor by just decreasing the feature size. That's Dennard scaling. And Dennard scaling ended around 2007, 2008. So we can't continue to reduce the size and get a faster clock cycle and enhance the performance. The clock cycle today is roughly frozen at 3 gigahertz, and that's because of the breakdown of Dennard scaling. The chip heats up too much if we try to enhance the cycle time of the chip, and we end up with a much hotter chip that we couldn't sustain. The other thing that happened, of course, there was an economic downturn that happened around 2007. But it's interesting that the laptop I use to give this talk, I can run the benchmark on, and I can run the benchmark on my laptop, and I get about 166 gigaflops out of my laptop. And my laptop is primarily used for giving talks and reading email, to be honest, but it's quite a stunning number when you think that not too long ago, the fastest computer in the world was actually slower than my laptop. The machine that was at Los Alamos National Lab used to do the nuclear weapons calculations was slower than my laptop. So that's again quite a stunning achievement in terms of the technology that we have today. So again, we see this the curves are changing because of a number of reasons. Another reason is that people are holding on to their computers longer. So the lifetime of these computers on the top 500 list is being extended. And again, that could be an economic, that could be caused because of an economic effect in terms of people just not wanting to make that investment in terms of new machines. I'm going to pause here to see if there's any questions, and I'll have a sip of water.
There are no questions in the chat, but we welcome anyone who'd like to unmute.
Yeah, I have a quick question.
Yes, please.
Do you think that matrix calculations are still a good benchmarking problem for determining the fastest?
That's an excellent question. That's an excellent question. In particular, I'd say do I think that dense matrix calculations are a good way to characterize these computers? So most of the operations, so again, you have to understand the historic standpoint of the benchmark. Back in the late 70s, floating point was very expensive. Today, our processors are over provisioned for floating point. You probably know or will learn about GPUs and having tremendous capabilities in terms of doing floating point operations. So today, floating point is cheap. They're over provisioned in our hardware, and doing things like matrix multiply perhaps are not the best thing and really don't reflect what's being done on these computers. So we have another benchmark in mind, and I'm going to show you that benchmark in a moment. But let me just carry on with this historic statement. The first petaflop or first teraflop machine was at Sandia. The first petaflop machine was at Los Alamos, and we're hoping for an exaflop machine sometime very soon. China says 2021, US says 2021 or 22. There's been a lot of speculation that China already has an exaflop machine, but because of the political situation, they're not exposing that machine. And they're not exposing it because there could be some backlash in terms of technology that is currently flowing to China, where if they turn up with an exascale machine before the US, the US may take some, may in fact impose some sanctions on China. The US has done this before, so this would not be a new thing. But we have rumors that China actually has 2 exascale machines in production today. So let me carry on here. This is the list of the top 10 machines. I'm not going to dwell on this. I just want to give you a sense here. Number 1 is Riken Fugaku's machine, 7 million cores. So if you're programming this machine at scale, you would have to write a program using MPI that would have to coordinate 7 million processes, is the way to think of this. Is one way you could program this machine. Most people would not do that, but that's one way of doing it. This machine achieved 442 petaflops. That's 82% of the theoretical peak performance. Again, about 30 megawatts, and its efficiency is 14.8 gigaflops per watt. So you want to have that number, gigaflops per watt, as high as possible. If you just scan down here, you see this machine here, the newest machine on the list. This machine at Lawrence Berkeley Lab uses HPE, uses AMD processors together with NVIDIA's A100 and Cray Slingshot interconnect, achieving a very good gigaflops per watt. The machines in red here use accelerators. Many of the machines in the top 10 use accelerators, but we have machines which just use Intel processors, like this one. The Sunway machine has this lightweight core, and the Fugaku machine is actually based on ARM, but it's an ARM which has ARM processor which has vector instructions. So they've modified the ARM processor to use vector instructions. So a smattering of machines. I'm not going to dwell on this. China has the most machines, followed by the US, followed by Japan, followed by a number of countries here. I see that my chart here has got squished. This is this chart here. We have 500 rectangles. Each rectangle represents a computer, and the area of the rectangle represents the performance. So this green blob here is the number 1 machine, followed by the number 2 machine, followed by the number 3 machine, and then the number 4 machine over here. So that's one way to characterize these machines. Not surprisingly, if you plot the top 500 machines by performance, you get a graph which looks something like this. You have a very steep, very few machines with high performance, and then a lot of machines at this long tail here. So I would say, we have too many machines. 500 is too many machines to characterize supercomputing. Maybe we need something which is looking at the top 100 or maybe even the top 50 machines to characterize things. Fugaku is based on an ARM processor. It has 48 cores on its node. One node has 48 cores. Vector instructions are there. It has a very fast interconnect. It has the ability to do 64, 32, or 16-bit floating point operations. It can reach close to 2 exaflops for exascale operations. this one machine has 16% of the performance of the top 500 computers. This is the number 2 machine at Oak Ridge. I just want to show you its characteristics. It's based on a node. That node has 2 IBM Power 9 processors plus 6 NVIDIA V100 GPUs. So the machine is a hybrid machine based on that. If you just use the if you didn't use the GPUs, you would only be able to get 2.3% of the performance of this computer. Most of the performance, 98% roughly, comes from the GPUs. So you have to be using the GPUs to extract the performance. Because of the GPUs, you could do 16-bit floating point operations. That's becoming an interest to many people, using reduced precision to carry out the computations. And there the peak performance is about 3 exaflops. Okay, so getting back to the question that was asked, doing this matrix computation, is that really a way that we should be characterizing these computers? So let me say that most of the machines, at least the machines in the Department of Energy, are used to solve 3-dimensional partial differential equations. And those 3D PDEs are characterized by solving a sparse matrix problem. So we still have a matrix problem, but the matrix is sparse, so large and sparse. And we don't use a direct method like Gaussian elimination. We use an iterative method, a method that basically takes a matrix and an approximation and iterates with the matrix and that approximation to get a better approximation, and does that by doing a number of matrix vector-like operations. So that's sort of the core of this particular benchmark, is doing that operation. So the benchmark is based on doing a conjugate gradient algorithm to solve that large sparse system of equations. That large sparse matrix, again, characterizes many of the problems that are run on the high performance machines, or at least the machines at the top of this chart. And this is the results of that benchmark. So this benchmark here now is HPCG, not the top 500. The machine from Riken is still the #1 computer. And it ran the benchmark at 16 petaflops. So notice that the LIMPAC benchmark ran at 442 petaflops. The sparse benchmark ran at 16 petaflops. So that's sort of the distinction here between these two benchmarks. And you could see what's happened. The #2 machine for this particular benchmark is the machine at Oak Ridge National Lab, followed the machine at Lawrence Berkeley. But take a look at the percent of peak. So the LIMPAC benchmark was getting around 75 to 80% of the theoretical peak of the machine. This benchmark is exposing only around 3% or less of the theoretical peak of these computers. The best one is the machine at position 10 here, and that's a vector machine based on a traditional vector architecture from NEC. So it's getting about 5.6%. And that machine is characterized by having a lot of good bandwidth for moving data between the architectures. The Fujitsu machine also has that, and that shows up in this percent of the theoretical peak performance. So this is a chart which looks at the theoretical peak performance. That's the black dots. The green dots are the LIMPAC benchmark that's doing Gaussian elimination on a dense matrix. And the blue dots are the results of doing this HPCG benchmark, doing a sparse matrix computation. So you see the great difference between those two. So I'd like to characterize these benchmarks as sort of bookmarking bookends for the way your performance, for the performance that you will see on these computers. Again, the lower end is more typical for the kinds of calculations that we might do for solving large-scale partial differential equations. Okay, I very quickly are going to pass through this. There's a great interest in low precision, and that's driven by deep learning. So machine learning, deep learning, neural networks can get by with 16-bit floating point arithmetic. So we see a lot of hardware coming out which uses 16-bit floating point arithmetic. A lot of companies then use that hardware to solve those machine learning problems. And we in the scientific industry are interested in this because we do less communication, there's less memory traffic, less network, it reduces the memory footprint, there's more flops available to us. The theoretical peak performance for 16-bit is usually 4 times that of a full 64-bit precision. So if we can get away with it in our computations, we want to use that lower precision as much as possible to get the fastest results. And a number of people have put together algorithms which can exploit that. And in some cases, we can exploit that low precision and through some mathematical techniques, extend the accuracy to get much higher accuracy than we deserve from using that 16-bit arithmetic and still come up with a solution which is much faster than if we had done the whole calculation in 16-bit. So again, 16-bit, 32-bit is interesting. We see factors. The cell processor had a factor of 14 between 32 and 64-bit floating point. Apple's ARM Cortex A9 processor has a factor of 7 between 32 and 64-bit. And NVIDIA, we see a factor of 16 between the 16-bit and the 64-bit floating point arithmetic. So you could see that people might be drawn to that because of the effects of higher precision. So we have another benchmark, and this benchmark is called the HPAI benchmark, and it exploits 16-bit arithmetic. It exploits 16-bit arithmetic in factoring the matrix, and then it uses an iterative method on a dense matrix to recover the solution back to 64-bit accuracy. So we're going to factor a matrix in 16-bit. That's where most of the computation occurs. Order n cubed operations are being done at this very low precision. And then we use an iterative method with that 16-bit factorization as a preconditioner. And doing that iterative method in 64-bit accuracy, we're able to recover the solution and get to a solution that's as accurate as if we had done the whole thing in 64-bit computations. And that benchmark goes by the name of HPAI. And when you run that benchmark on the Fugaku system, we see 2 exaflops is the performance that we can extract. And that's 4.5 times faster than we saw from the LIMPAC benchmark. And you can just go down the list here and see what's happened. So I'm going to conclude by saying that the hardware is constantly changing, going from scalar to vector to distributed memory to accelerators to mixed precision. We have these computer revolutions that are going on: high performance computing, deep learning, edge computing, and artificial intelligence. I didn't have time to talk about that in detail, but that's a lot of that's going on behind the scenes here. Algorithms and software usually follow the hardware. So the way it works, I've been in this business 50 years. People throw a piece of hardware, new hardware, over the fence, and they say, see what you can do with this. And the software people and the algorithms have to be organized to fit on that new hardware and make it run efficiently as possible. So there really is plenty of room at the top, a riff off of Feynman's lecture a number of years ago. There was an interesting paper published by Charles Leiserson and company that appeared in Science last year that talks about this, about how we can extract performance from our algorithms on modern architectures by exploiting some of these things. So at this point, I'll stop, and I'd be happy to answer any questions that you might have left.
Thank you so much, Jack. Really wonderful lecture. We have 3 questions so far in the chat. And in fact, the most recent one really resonates with the point that you were making in the last slide. So I'll ask Salmik, Dana, would you unmute and ask your question? And then we'll proceed to the other questions after that.
Hey, Jack, thanks for the great talk. I asked the last question. I wanted to kind of understand how, the solvers were being developed with, all the supercomputing power that was being added on and on. And was there some sync between like those two communities? Were they talking to each other? And there's also one follow-up question. How do you see the development of like direct solvers, as opposed to iterative solvers? Thank you.
Okay, good. Those are good questions to begin with. So again, we have this hardware in place, and there's this notion of co-design. So we meaning the people who are dealing with the Department of Energy's exascale computer program, have this notion of co-design, where it was intended for the hardware people to get together with the applications people, to get together with the software developers, to build a system that can work coherently. Well, that hasn't really worked, I'll say. It works in a very superficial way. The application people and the software people get together all the time, and they're very closely integrated in how they move forward and how they can effectively use the hardware. But the hardware gets thrown over the fence, and we have to sort of figure out what the best approach is for solving problems on these machines. And that's a process which is not automatic. It takes a number of years after the hardware is deployed before we really understand how to effectively use those machines and produce very efficient solutions to the problems. And that causes us to rethink the algorithms. So there's algorithmic development that occurs. There's research that occurs in developing new things to be done. There's a lot of work today going on how we can effectively use things like the GPUs, how we can effectively use the ideas of mixed precision, so we can exploit that in our basic algorithms, and how we can move things forward with the hardware that's presented to us. So it's a mixed thing in the sense that if there was really a co-design, we would get together and sort out things, but the hardware just moves so quickly. I think it's just hard for them to pause while we try to have input into that process. They just develop something and throw it over the fence, and we're stuck with it. We make small changes to the hardware, I'll say, are perhaps possible, but large changes are really not. And it's left to the software and the applications people to figure it out. And we're doing a pretty good job with that. In terms of dense solvers, so there are many problems which need dense solvers. Those aren't the high order bits of computational science, however, but there are problems that need to solve dense systems of equations, and solve dense eigenvalue problems, and solve dense singular value decompositions. Those are all important problems. And most of the work, as I've said, is really taken up by solving large scale partial differential equations, and doing that by an iterative method. Those matrices are typified by being sparse, having some sparse structure to them. And algorithms have to be developed which effectively exploit that sparsity.
Thanks for that information. I will just remark that on August 10th, there will be a track on numerical software. So these kinds of issues will be discussed by other speakers during that track. All right, next question is from Julio Mendez. Julio, would you like to unmute? And
thank you very much. Such a wonderful lecture. Thank you very much. I really enjoyed. I have a question in regards of how these tests or benchmarks are performed. So I understand that is basically an algorithm that is being tested throughout the different architectures. But my question is more, how can you or committee make sure that all these applications are similar? You mentioned something interesting about 7 million or 1 million cores. I don't remember the number, but it was very complicated. It is in fact very difficult to really work with such a high number of cores. How does the committee really make sure that all these applications are similar or standardized in order to come up with this list of top 500 machines? Thank you very much again for such a beautiful lecture.
Okay, thanks for that question, Julio. Let's see, so again, there's some ground rules for the benchmark. It says you have to use, for the LIMPAC benchmark, the top 500, you have to use Gaussian elimination with partial pivoting. You're allowed to do an implementation as best you can. We have a reference implementation. So we have an implementation which uses MPI. It does message passing, of course, and you could use that benchmark as a starting point for your implementation. So if you're a computer vendor, for instance, or if you have a new computer and you want to run the benchmark and enter it into the top 500, you might start with that reference implementation, which does MPI. It scales, it runs on large numbers of processors. It can run up to millions of processors and has been used there. And then make changes to it which retain the basic algorithm of Gaussian elimination with pivoting, partial pivoting, but optimizes the way in which data is passed around, or optimizes the way in which the matrix multiplies, or some of the other very, very basic operations are done. So there's scope for optimization, but the ground rules say you have to use that same algorithm. So of the 500 machines over the past 23 or 27 years, whatever it's been, have all used that algorithm, Gauss elimination with partial pivoting, the thing that we learned in high school for solving systems of linear equations, and have implemented it in slightly different ways, optimizing it for the hardware. The HPCG benchmark has similar rules. You have to use that. We have a reference implementation for that. You can modify that for the specifics of your architecture and run it on your machine to see what kind of performance you get out of it. So that's sort of the very general way of things proceed. There's a set of ground rules. The benchmark itself has a way for self-checking to make sure you've gotten the correct answer. Many people use this benchmark as a way to debug the hardware. So, these are new machines that are coming up and being stood up, there's lots of flaws in the machines. Hardware is bad, connections are missing, perhaps wires don't make sense, and they run the benchmark to sort out any of the mistakes that might have been made in the hardware. And most often they find something and correct it before they actually submit an entry result because they haven't got the right answer. So I'll leave that question there.
Thanks, Jack. So I defer to Ray to let us know if we should continue with questions or stop, since we're nearly at the top of the hour. There are 3 more questions in the chat at this point.
We can take a few more minutes, Lois.
Okay, great. Next up is Mahalo Issaquah.
Hi, Dr. Dongarra. You showed a couple of slides on what percentage of theoretical performance we are achieving for different systems. What I'm interested in is historically, how has that changed, and are we going down or up?
Right. So, okay, that's an interesting question. If we take a look at the top 500, there have been outliers, I'll say, which have been able to extract more than 75 or 80% of the theoretical peak performance. So today, if you take a look at that chart of the top 10 machines, they're roughly in that range between 70 and 80% of the theoretical peak. I can remember a machine which was above 90% of the theoretical peak. And when I first saw that number, I thought they had a mistake. I couldn't believe that they were so efficient in terms of their architecture. It was a new machine, but after investigating, it was a very efficient implementation. They had a lot of bandwidth associated with the machine, a lot of movement of data. So if you want to make a machine and to get a high performance, what you want to do is to have high performance floating point and also high bandwidth from memory. Those are the 2 things which cost the most. In fact, the memory, passing data from memory into the processor where the operations are done, that's where time is really consumed. So think of it like this: on modern processors today, to do floating point operations, to do 2 floating point operations, it takes maybe less than 1 cycle. So we have multiple functional units doing it simultaneously. So we can retire something on the order of 16 floating point operations, 32 floating point operations per cycle. That's on an Intel processor. So every cycle you can complete 32 floating point, 64-bit accurate solutions. That's a tremendous amount of floating point capability. I'm not even talking about GPUs. This is on a standard Intel processor. GPUs can do much more than this. However, moving data from memory from primary memory through that hierarchy memory to the level 3, level 2, level 1 cache and into the registers, that can consume more than 200 cycles on a machine. So we're comparing 200 cycles on a machine just to move one piece of data through that memory hierarchy before it can first be used, where that processor is ready to do 32 floating point operations per cycle, completing them. So that's an incredible mismatch. And the only way to compensate for that is to get reuse of data in cache. So that's really where we have to exploit that. If you wanted to build the fastest computer, you would have much greater bandwidth, but that's very expensive. And that's the reason why it's not done. So that bandwidth comes at a very high price. And architects, compensate for that by giving us levels of cache and putting the memory as close to the processor as possible. So today we have, memory that's actually on the chip today, a stacked memory, 3D memory, very close to the processor itself. So it doesn't have to take all that time to come from some distant memory location.
Thanks, Jack. This discussion really leads nicely to the question that Guillermo Travis has. Guillermo, would you like to ask your question now?
Yes, thank you very much. So my question is, well, how do you see the future of supercomputers? Do you think there will be a limit when we cannot afford that much power in them, or there will be a limit in how can we synchronize or communicate this processor, this large amount of processors? How do you see the future of supercomputers in the next decades?
So that's an interesting question. Where do we go from here? We're reaching some fundamental limits. Moore's law is slowing down, Dennard scaling ended. We have limits in terms of what we can put onto chips, what the feature size is. We're reaching fundamental limits there. What happens next? Well, what we've seen is that we've replaced the processor with a GPU. That is, we've attached the GPU to it. So we've had this attached thing, and it does work very much like an attached thing. You have to send data from the processor's memory over to the GPU memory, do the operation there, and then send the results back to the processor. So you offload stuff and then bring it back. That's a time-consuming thing in itself, but that's part of the way we deal with it. What's going to happen in the future? I would predict we would have more things added to that list of things we put on our machines. So today we have accelerators in the form of GPUs. We can think about some kind of, in the future, not next week, some kind of quantum computer, which we add, where a quantum computer is not going to solve the problem as we know it, the numerical problem. Quantum computing does not give you an answer. It gives you a probability of an answer being around here. So it gives you a fuzzy region. And, if you ask the question again tomorrow, the same question, you're going to get a slightly different answer. So it's not going to give you a precise answer that we've been accustomed to, but it can give you a solution or a handle on the solution to different kinds of problems. So I could see that being added to the ensemble. We think about optical computing as another thing that we can perhaps add, using light to solve the problem. So think about the processor being, what happens when we interact these two beams of light, giving us something at the other end. So think about doing a matrix multiply where we have two streams of light representing the data coming into this optical computer, and the output of that runs very fast at the speed of light, producing the matrix multiply, let's say, at the end of that operation. Or we can think about neuromorphic computing being added to the list. Or we can think about FPGAs being added onto that ensemble of things that we use. So it's going to depend on what the application dictates. So what the application calls for, we can add them into this next generation, the future generation of computer, to help us solve that problem in a much faster, more economical way, perhaps.
Thank you very much.
Thank you, Jack. We'll lead into our final question from Phil Boarding. But before Phil asks his question, I'd just like to again take this time to say a deep, heartfelt thank you to Jack for speaking to us. And I encourage you, if you want to do an online clap using your icon, feel free to do that as we're wrapping up the session.
And
Thank you.
let me say that if you have questions that haven't been answered, you can send me email. I'll be happy to answer them. So what's the last question from Phil?
Okay, so you talked about applications. What applications today have runtimes that exceed algorithms? Let's talk about algorithms. What areas have runtimes that exceed 100 hours?
Okay, so I guess let me just preface this by saying the Department of Energy is investing in 3 exascale computers. These are 3 very large, expensive computers. Each of these computers, the hardware, each one of them costs $600 million. So these 3 exascale computers, one's going to go at Argonne, one's going to go at Oak Ridge, and another one is going to go at Lawrence Livermore National Laboratory. And that's going to happen in the next year or 2. Those 3 machines are going to be used by the Department of Energy to solve some of the most challenging problems that we have. And those problems can easily take over 100 hours to solve. So, we're going to be using these machines. In some cases, these machines will be used to solve many problems at the same time. So there'll be time sharing that goes on in the machines. We have many problems running on the machines, but occasionally one application will be able to run on this supercomputer. And that take the whole machine using all of the processing capability to solve that one problem. And that solution may easily exceed 100 hours. And that brings about many challenges in terms of running a problem for 100 hours. So you want to be sure that if a problem is going to take 100 hours, that your application doesn't die at the hour, at 70 hours, when you're almost to the end of the computation. We can't have the computer fall over and lose everything. So the application must be responsible for doing some kind of fault tolerance in the algorithm. And that fault tolerance usually takes the form of a checkpoint. So you do a checkpoint, and that will allow you to restart from that checkpoint if the machine failure occurs. Or if you get tired of running or your allocation runs out after, let's say, 25 hours, you can do a checkpoint and then come back and then later go on and solve your problem. So what problems are we talking about? The Department of Energy has a list of, I think, 23 or 26 applications which they are targeting for exascale computers. And those applications run the gamut of things. Think about better combustion engines. So trying to build a better conventional engine, building things more efficient, materials. Look at drug design. Look at doing things for nuclear safety. I would guess somebody is going to be giving a talk about the ECP project during the course of these 2 weeks. And you're going to be hearing about some of these applications in that time. But the Department of Energy is making a huge investment. So there's $1.8 billion going into 3 computers, and they're spending $1.8 billion on the applications and the software that's necessary to run those applications on those machines. So it's a tremendous investment that's taking place now. That's going to be complete. That's going to be the machines will be ready in about a year, and the ECP program will be running those applications over the course of the next 5 to 10 years, I would guess.
Thank you so much, Jack. So this was a really wonderful way to help kick off the first day of ATPESC. Now turn over the program back to Ray.
Thanks very much.
Thanks
guys.
again, Jack.
Yes, thank you, Jack, and thank you, Lois. Jack, did you want to pop your email address into the chat so they know where to reach you?
Yes. You could just Google me or use that.
And Jack's slides are already linked off the agenda if you want to reference them. And thank you once again for coming. We'll say goodbye now and move back to the hands-on with Jehan.
Okay, yeah, let me share my screen again. Okay, do you see my slide?
Yes.
Okay, so yeah, we just finished the data and data GPU hands-on. Hello world. Without hello world, we cannot run the exascale, right? So I just have only one part for the Cooley. So before moving to Cooley, so previously I had my slide has long information, so I put the Q ATPESC 2021 for the data GPU, but it turned out the training is correct Q for the reservation, right? So I just updated this information, and I uploaded the updated the slide deck and here. So yeah, please download it again and use that. Let me go back to the data GPU side here. So previously, what I showed you was in order to use the Theta GPU, you need to do the SSH from the Theta to Theta GPU login node, right? And then you can do the QStat or the test or something, right? So there's another way to use the Theta GPU from the Theta login node, which is I didn't add it to here, but because there is some people may have some confusion on this mode, but just for your information, let me show you how it goes. Okay, so this is so I just log in the Theta login. In this case, I have a Theta the login, right? So if I do the QStat, I see the job on the what happened on the Theta now, right? So in general, so what I showed you to use the Theta GPU is SSH and Theta GPU SN1 or SN2, right? So this is one way. The another way could be there is a login node. There is a module on the Theta login for the Theta GPU. This is really complicated, but Theta. If you load the Cobalt and the Cobalt GPU module, so you still on the Theta login here, right? And then if you do the module list, what you see is so you have all the modules for the Theta, and then you have a Cobalt GPU module, right? So with this module, even though you are on the Theta login node, you can launch your job on the Theta GPU. So if I do the QStat here, now instead of seeing the jobs on the Theta, you are seeing the Theta GPU jobs, right? So the reason I didn't add this this instruction to our hands-on session is it's kind of confusing for the first-time user, because if you do the module list, we still see a lot of modules for the Theta, but now actually you are using Theta GPU from the Theta login. So because of this reason, I didn't add it to you. So if it's too confused, you can just do this SSH and Theta GPU SN1. Okay. So yeah, my sysadmin mentioned that this way could be another way to access the Theta GPU. So I'm just sharing to you. So the remaining part